Today we're going to be talking about building quadratic functions from geometric patterns. So our first question is all about quadratic expressions in area. So figure A is a large square. Figure B is a large square with a smaller square removed. And figure C is composed of two large squares with one smaller square added on. Okay, and so based on this information, we are going to be able to fill out this table, where we're going to write an expression to represent the area of each shaded figure when the side length of the large square is as shown in the first column. Okay, so if we have this large square and each side is 4, well, to find the area of a square, we take length times width, or the side squared. So that means that this would be 4 squared. And you could evaluate that if you want, but it doesn't matter in this case. The area of figure B then would be that same thing, 4 squared, but then we're subtracting out this little square, and that little square has an area of 1 times 1, or 1. So 4 squared minus 1. This one, we have 2 of those 4 squareds because we have 2 of the big rectangles, and then we're adding 1 from the little square. So let's see what happens if our side length is x. We have x times x, which would give us x squared for figure A. Figure B, we would take that x, multiply it by itself, but then again we're still subtracting that little square inside that has an area of 1. Here we would take 2 times the x squared of the regular square, and add the 1 for the little square. For if we had a side length of 4x, we would take 4x times 4x, which gives us 4x quantity squared. You could also write that as 16x squared. The middle one, we would take 4x and square it for the big square. And again, we're subtracting 1. You could also, evaluate that to be 16x squared minus 1 if you wanted. And then here, we would have 2 times, let's say 4x squared, okay, and then plus 1. So again, you could make that be 16x squared multiplied by 2, 32x squared plus 1. You could also write that. That's an equivalent statement there. Here we have x plus 3 as the side length, so we would have x plus 3 squared because we're multiplying that length times itself. Here we would have that side length squared for the square minus the one that's inside. And last, we would have 2 times the x plus 3 squared because we have 2 of those same size squares plus the one that's happening on the outside. Alright, so let's look at expanding squares, okay? If the pattern here continues, so we have step 1, step 2, step 3. If the pattern continues, what will we see in step 5 and step 18? Okay, so take a look at what's happening in this. So in step 1, we're seeing a small square in the middle, a 1 by 1 square, and then 4 squares around it. In step 2, we're noticing a 2 by 2 square and 4 squares around it. In step 3, we're noticing a 3 by 3 square and 4 steps around it. So in step 5, we would have a 5 by 5 square with 4 squares surrounding it, or around it. For step 18 then, it does not look like 18. Step 18, we would have an 18 by 18, oh my goodness, 18 by 18 square with 4 squares around it. And by around it, we're meaning like they're on the corners. Okay, so you could also use that vocabulary as well. So how many, the next question then is how many small squares are in each of these steps, and explain how we know. So if we had a 5 by 5 square in the middle, we would have 5 squared, and then we have the 4 small squares around it. So then that would give us 29 squares. So I guess we should say this is step 5. For step 18, we would have 18 times 18, or 18 squared, plus the 4 small squares around it, which would give us a total of 328 squares. Okay. Part 2 of this question says write an equation to represent the relationship between the step number n and the number of squares y. Be prepared to explain how each part of your equation relates to the pattern. Okay, so you could make a table if you wanted here, but if we're looking at this, so let me bring this back up for a second. In step 1, we had a 1 by 1 square in the middle, and then we had 4 added. In step 2, we had 1 squared plus 4. Here in step 2, we had a 2 by 2 square, so 2 squared plus the 4 on the outside. In step 3, we had 3 squared plus 4 on the outside. In step 5, we had 5 squared plus 4 on the outside. In step 18, we had 18 plus the 4 on the outside. So if this were the nth step, we would have y equals, they told us to use y for the number of squares. We're taking the step number squared and adding 4 to it. Okay, so this is because we have the n by n square in the middle. So n by n square in the middle. And this is for the squares on the outside. Okay, the squares, the 4 squares that happened on the sides, or on the corners, I guess we'll say. All right, so what if we're looking for a different situation? What if we want to sketch the first 3 steps of a pattern that can be represented by the equation y equals n squared minus 1? So if we're using that whole idea of n squared, that means that it's the first step, okay, it would be 1 squared minus 1. Well, if we're actually doing that in step 1, we would have nothing there, right? 1 squared minus 1 means that there's nothing there. So in step 2, if we take that 2 and plug it in for n, 2 squared is 4, 4 minus 1 is 3. So if we imagine us having this 2 by 2 square, we're only going to have 3 out of the 4 because we're getting rid of 1. Okay, so it would only actually be this shaded area here. So then step 3, if we imagine having a 3 by 3 square, here we have 1. So we have a 3 by 3 square, but we've gotten rid of that top one. So here we have 9 minus 1, or just 8. Now this is just one representation of what this can look like as you go. But there's one for n squared minus 1. You can always plug in the numbers, the step number, into your equation to kind of see what it would be as well. Okay? All right. So the next thing we're going to talk about are growing steps. Okay? And so this one, we have step 1, that's 3 blocks. Step 2 is 2 by 4 blocks. And step 3 is 3 by 5 blocks. So it says to sketch the next step. So step 4 in this pattern, if it went 1 by 3, 2 by 4, 3 by 5, this next one would need to be what? So we would need 4 by 6. So we need 1, 2, 3, 4, and then 1, 2, 3, 5, 6. Okay, so step 4 would be a 4 by 6 in this. Okay, so Chiron says that the pattern is growing linearly because of this, as the step number goes up by 1, the rows and the number of columns also increase by 1. So step 1 here we had a 1 by 3. In step by 2 we had 2 by 4. Step 3, 3 by 5. Step 4 we had a 4 by 6. And so do you agree with that? We need to explain our reasoning as well. So with this, let's count the number of blocks. So here we had 3 blocks. Here we have 8 blocks, 15, 24. Is this going up by the same amount every single time? Is the number of blocks going up? So from 3 to 8, that's adding 5. 8 to 15 is adding 7. So right now we already know that this is not linear. So no, because the number of, we'll say small squares is not going up by the same amount each time. All right, so then to represent the number of squares after n steps, Diego and Jada wrote different equations. Diego wrote the equation f of n equals n times the quantity n plus 2, and Jada wrote the equation f of n equals n squared plus 2n. Are either Diego or Jada correct? And we need to explain our reasoning. So where could Diego have gotten this? If we're looking back up at this pattern, he's saying n. Remember, n is counting for the term number, or the step number. So here we have a 1 by 3. Well, 3 is the same thing as taking 1 and adding 2 to it. So it works for the first one. Does it work for the next one? We have 2 times 2 plus 2, which is 4. 3 times 3 plus 2, which is 5. 4 times 4 plus 2, which is 6. So yes, Diego is correct. Okay, so yes, Diego is correct. All right. For Jada, we're saying n squared plus 2n. So we're having an n squared plus 2 more blocks. Okay, 2 more times the step number that we're on. For step 2, we have a 4 by 4 square plus 2 times that, which would be another 4, which makes our total 8. For step 3, we have a 3 by 3 square, which is 9, plus 2 times that 3, which is 6. Okay, and it also works for step 4. So we said, yes, Diego is correct, and so is Jada. Okay?